So the format of the evening is just before, well, the next thing that's going to come up is Jerry has apparently got something that's going to take 30 seconds to tell us about. So we'll in a moment move over to him. And then that's going to be followed by Martin Weston, who's going to be giving us his monthly night sky review. Then I'm going to pass over to Jerry, who's going to introduce tonight's speaker, our guest of honor. Roger's going to talk for about an hour. Well, I won't talk anymore there, I'll leave that to Jerry, but there will be a time for a question and answer session after that. When that's finished, we've got something a bit unusual. We've got some special visitors from, as I said earlier, from Argentina. They're going to tell us about an exciting project that they're developing in their home country. And we would expect the meeting this evening to finish around about 10 o'clock, maybe a bit before, maybe a bit afterwards. So that's the plan for the evening. So I'm now going to pass you over to Jerry, and I'm going to unmute him. And you should be able to take control of the screen, Jerry.
Okay, thank you. Hi, everyone. I just wanted to very quickly mention something that's happening tonight. This is the 9th of September, and at 8:20 tonight, the time and date will read 2020 on 09/09 of 2020. There you go, just a bit of fun. Back to you, Alan.
Okay. Just scrolling down my list for Martin Weston. I'm going to unmute. So over to you, Martin. Can you take control of the screen?
Okay, thank you very much,
There
Alan.
you go.
Can everybody hear me okay? Hi, everybody. Lovely to see you all after our break over the summer, which has been a bit shorter than we normally have, but feels unlike last week that I was giving a chat about what was in the sky, but try not to repeat anything if I can help it. My last talk, I was talking about Jupiter and Saturn going into opposition, which is now obviously passed, but we've got another planet going into opposition shortly, and I'll be talking about that later as well. But before I do that, I wouldn't mind just going into Stellarium. Let's see if I can share my screen. Hang on a second. If that's possible. There we go. Share it. Let's try that. So hopefully, if I get this right. Does everybody see Stellarium there? Good, good, good. Okay, fantastic. Okay, so this is looking at tonight, and I was just going to point out that Jupiter and Saturn are very close at the moment. Again, they've been, obviously this, because they're moving in similar orbits, there's not been much change in the last couple of months, but they're further around the sky, still a bit low, but still nice and bright and worth a look. So anybody have a look in the southern sky, that's where they are in about an hour's time. So you look directly south, you'll see them quite clearly. And what I was going to do from that point, just go up a little bit. Now, something that I've been looking at quite a bit over the last month or so is Cygnus, the Swan, because it's almost directly overhead. And if anybody who's interested in imaging, this is when we get our clearest images of some of the nebulas and items of interest in Cygnus. Cygnus runs almost directly through the Milky Way, so it's a very, very star-struck area. And there's some very interesting, there's a North American nebula, which is just off to the side here. And there's Crescent Nebula here, and there's quite a bit of stuff in here. So this is a really good time still going forward to be imaging anything which is almost directly overhead, because you're obviously looking through an awful lot less atmosphere than you would be normally. Another thing I've been imaging here in Lyra is the Ring Nebula. There's quite a few planetary nebulas, and I'm sure, I don't know if I've explained about planetary nebulas before, called planetary nebulas because they appear spherical in shape and they were assumed to be planets, but they are actually remnants of a star similar to our own sun, where it's cast off its material at the end of its life and then shrinks into a white dwarf at the center. So they're quite an interesting object. But what I really wanted to talk about was we're now transisting or transforming to the autumn sky, and we're getting some new constellations coming up which are worth looking at. And I noticed the other day when I was out in the evening that I could see Seven Sisters coming up about midnight. So that always to me means that not far behind is going to be Orion, and Orion is quite an interesting thing for people to look at because it's got one of the brightest nebulas in the sky. So I'm going to just push it forward a little bit here if I can. Let's see what time. Let's see if we can get Orion to come up. So there's the Hades there. That's just north. That's just above Orion. And as you can see, the bow of Orion just coming up here. So here's Orion here, there. So, and there's Gemini, Castor and Pollux. And that's showing at the moment 1 o'clock in the morning. So, oh no, 10 o'clock. No, 1 o'clock. So it's still quite a way off yet, but that will be getting higher and higher as the month goes on. And I'm sure that the images in our club will be busily taking pictures of Orion Nebula and the Horsehead Nebula. Okay, so I'm not going to spend too long going through the night sky. I want to really talk about the opposition of Mars, which is coming up very shortly. So here we are. That's where Mars is going to be. As you can see, I've moved Stellarium onto this date. That will be at its closest to us in opposition. So I'll just go into a little bit more detail. So this is how it's actually looking. So it's just an interesting little screenshot that I got off the internet, and it's showing where we are. It shows the dates here and where we are. So that's where Mercury, that's the Sun obviously, that's Venus there and Earth, and there's Mars there. So eventually we're going to be in here, we're going to be lining up with Mars. Obviously Mars is going to move a little bit further this way, we'll move that way, and we're going to be in a line. And that's what it means when we're in opposition. So we'll be looking at a full face of Mars being lit by the Sun obviously. So a little bit about Mars there. So Mars in opposition occurs at the end span of 91 days. Three bright outer planets, Jupiter, Saturn, Mars, passing the opposition as I spoke earlier on in the year. So that image there was taken by Steve, one of our committee members, I believe last night. So it's a lovely picture. Well done, Steve. I think everybody thinks that's superb. I don't tend to do planetary imaging myself, so it's something that is beyond me, I think. But that is a beautiful picture, Steve. Well done. So that's what Mars is looking like at the moment. So no dust storms I can see on there. It all looks pretty clear. It's quite a bit of detail there. So yeah, that's really interesting. We'll move on to the next slide. So this just shows a little bit about retrograde orbits. I'm trying this time to just explain what a retrograde orbit is for those who don't know. And this goes back to right back to the Greeks, when they noticed that all the stars and all the objects in the sky moved across the sky in one direction, but the planets seemed to move in their own strange directions. And one of the things they noticed about the outer planets was that this retrograde retrograde movement. So the Mars is moving along here nicely, then all of a sudden, at this point, it stops and starts going backwards. And then eventually comes back round forward again. And they tried to come up with all theories of why this was happening, which I won't go into at the moment. But what I was hoping to do is just briefly explain what the cause of that is when we look at Mars in the sky. So there's another image there of the retrograde orbit. So Mars opposition occurs 72 days after it passes its orbital point closest to the Sun, and that's known as the planet's perihelion. While the previous opposition occurs 49 days before perihelion. So just what I've managed to do is download off the net a retrograde explanation. So let's see if I can stop this share and do another one to show how this works. I do hope this works. So if I just start this, hopefully it'll work. No. Typical. No. Best laid plans of, let's do a restart. So if that works. Oh, try again. So here we are. So this is a brief explanation. So there, as you can see, our planet is moving faster than Mars because we're on an inside orbit. And this is our view of Mars, and this is why it appears to go backwards, because we actually overtake it. But if you watch the way it goes, I'll run that again just to restart. So as you can see, it's moving, and then it appears to stop, and then runs backwards until we overtake it, and then it starts to move forward again. So I hope that's a good explanation of what's actually happening. Okay, is there any questions? No, no news is good news. But if there's no questions, I don't think there's any questions, Alan. If not, I'll pass you. Do you want to pass it straight over to Jerry?
Yes, thank you very much indeed, Martin. That was really lovely, and especially explaining that retrograde motion, which is always a bit of a baffler. So if you'd now like to pass over to Jerry, that will be absolutely fine. Thank you, Martin.
Up to you then, Jerry.
Thanks very much, Martin. Well, this is the first session of our new season, 2021 season, and by tradition, that means our speaker is Roger O'Brien. Now, I've actually forgotten when that evening class started. Alan, you can help me out there.
2004.
Right. 2004, a small group took part in an evening course in astronomy, and they liked it so much they thought they'd like to carry on, and they formed a little group to do that, and the group grew over time until a few years ago it just started. Well, I think supernova is the appropriate term here, and we actually had to change venues twice within the period of just about 3 years because we kept outgrowing our venue. There were so many people who wanted to take part. I mean, now using Zoom, of course, that isn't a problem, but the person who preceded that that class was Roger O'Brien, and subsequently we decided that we would like him to become the Society's president, something that he says he's very proud of. His subject tonight is James Webb Space Telescope. Those of you who know something about exploration may sort of wonder why the telescope is named after someone who wasn't an astronomer, but there is an appropriate reason, especially when he starts to talk about the funding for it. And this is something we've been looking forward to for quite a while. Unfortunately, we've been looking forward to it for a lot longer. We expected to, because it's been delayed and delayed, so forth. But we do now have a new launch date. So to tell you about everything to do with the James Webb Space Telescope, please wave to Roger O'Brien.
Right, okay. Can I start sharing now, Alan? Okay. With any luck, you should all be seeing James Webb Space Telescope.
Yes.
James Webb in red and Space Telescope in blue. Oh, well, that's a start. You can all go home now. Right. Okay. Jerry's already mentioned the delays, and Alan and I actually debated whether we ought to postpone this to, make it conform with the subject, but we decided we would carry on and do it at the right time. And we've already had a joke about my fee being paid in 2045 rather than this year, just to sort of make things work. Okay, so Alan mentioned the launch date of 30th of March 2021, and I have to say that that actually even earlier on this year was beginning to be stated as at the earliest. And then over the weekend I checked up, and at least one NASA official has said that there is a new target launch date of 31st of October 2021. So it's moved a further 7 months back. I think the word target may be significant. They have, as Jerry hinted, and I shall go on hinting, they have had their problems with the James Webb Space Telescope. I can't go into all of them. Firstly, I don't know all of them. And secondly, the talk would last too long. I presume most of you don't really want me to do a list of delays that would take me something like 4 hours to go through. If you were prepared to listen to it, I'm not prepared to go through it. So I think we'll stick to just some examples. Now, this latest delay is, of course, partially due to COVID, which means that some of the factories have been working on shorter hours and haven't been able to have people in as many shifts and so on. There have also been some technical problems, but NASA are being a little bit cagey about the latest technical problems. In fact, they've been a little bit cagey about technical problems with the James Webb for a long time. The James Webb is an incredibly complex and ambitious project. I don't know whether anyone else feels this, but I sometimes wonder if they haven't got one technology too many at the cutting edge. I think some of the older projects, I mean, Cassini, for instance, which is, outstandingly successful, but the Cassini mission was entirely put together and launched and conducted on known, tried and tested technology. And there's a lot to be said for technology works. If you want another example, just look at the support of the International Space Station by the Russian Soyuz rockets. I know there is a sort of tendency to talk about Russian rockets as though, you know, you light blue touch paper and step back smartly, but they do go up like fireworks, you know. They have a 7-day launch campaign, not 5 or 6 months, but 7 days. Sorry, that's rude, the other way around. You know, 7-day launch campaign. They reckon if there was an emergency, they could launch a rescue Soyuz in 48 hours. There isn't another rocket system that could be done like that. Anyway, that's an example of how you do things with tried and tested technology that may look a bit out of date, but still works. Okay, let's go on. Oh, by the way, Jerry said there's a good reason for calling it the James Webb Space Telescope. James Webb was one of the NASA administrators, and many people feel that he was the guiding hand at NASA, while von Braun was the engineering hand that was getting the Apollo program off the ground. I don't know again about anyone else, but I do sometimes feel when I hear current projects, you know, I hear a little voice in my head saying, "Come back, von Braun, all is forgiven." You know, sometimes you do need a charismatic, dictatorial leading figure who also knows how things work. And this is, you know, what sometimes I feel is lacking. Anyway, let's press on. The announcement, by the way, was by this chap, Thomas Zurbichen. I don't know if that's how you pronounce it, but that's how I pronounce it. And that was exactly officially made on the 10th of June, 2020. And here is a famous illustration of the James Webb Space Telescope. This is actually a photograph of a model. I always think these things are rather fun when you have a photograph of a model of a spacecraft that hasn't yet been built. And there we are. Now you can see there's this huge sun shield thing. The main bus, the sort of control unit of the Space Telescope, is underneath. You can see a few of the solar panels there. Down here is a thing called the momentum panel, which I think is swung about a bit like you swing your legs on a swing in order to, in this case, to correct any swings you don't want to happen on the James Webb. The actual main part of it is this mirror here. And here's the secondary mirror, and there's a light baffle there. And behind the mirror is a module which contains all the instruments that will be used. And here is the sad bit. The project actually began in 1996 with a projected launch date of 2007 and a budget of 500 million. I think most of you will have worked out already that they didn't quite make the projected launch date. And I'm sure most of you will be aware that there has been a modest overrun on the cost. The latest total cost exceeds $10 billion. If you work it out, that is a cost overrun by a factor of 19. Now, even on a military hardware project, that would be exceptional. So I think we can say that the James Webb has set some rather gloomy records. And actually, if you look at the history of NASA in the last few years, it is quite clear that the James Webb has siphoned off an awful lot of funds that might otherwise have gone to other projects. Quite a few projects have been cancelled, although they've still managed to do some interesting ones. I mean, they have sent a probe to Jupiter. I've forgotten what it was called for them. Oh, Juno, isn't it? Yeah, that's gone to Jupiter, and they've got a probe, another probe on the way to Mars with Curiosity's big brother on board and various things like that. You know, that one's got a helicopter. The idea of being able to put a helicopter on Mars, I think, is amazing. You know, the thin atmosphere like that, I'm astounded that a helicopter will work, but apparently it will. Okay, so let's just remind ourselves, when this project was originally worked on, it was going to be launched by the Space Shuttle. Now, I'll just go back again for a moment. I've forgotten something to mention. This mirror here, which looks a bit of a funny shape, a sort of hexagon, is because it's made up of 36 hexagonal segments. In fact, it's very much the same design as the Keck telescopes on Mauna Kea. So originally, they were going to launch it with the Space Shuttle, and the mirror segments would be stacked inside the Space Shuttle cargo bay, a bit like coins in a till. And I must admit, the idea of having some automatic system to lift out each of these mirrors and slot it into some kind of framework and then adjust it and so on, always struck me as a recipe for disaster. Now, that may be me being a bit of a Cassandra, and if so, fair enough. But I think in the end, the fact that the shuttle was not available may have made the decision to go for a different launch system, may have made the whole project a little bit more practical. I hope it has anyway. Now, JWST, James Webb Space Telescope, will now actually be launched by the European Space Agency's Ariane 5 rocket. This is an incredibly sophisticated rocket. The European Space Agency rockets are renowned for being more powerful per ton of launch weight than anybody else's. In a way, it's a little bit like the Space Shuttle. You've got two solid fuel boosters here and a main section here. You can see this little blue flame coming out here. These are, you know, solid fuel boosters, as I said, and they produce a lot of jet here. You know, a lot of turbulent exhaust and so on. You can see these huge clouds of stuff there, but that central flame there is immensely powerful, and that will, as soon as the boosters have dropped off, that will drive the rocket up into orbit. Up here is a pod containing whatever was launched. Of course, this is a real launch, and I didn't even bother to find out which one. I just picked a picture of a night launch. One of the things that most of the space agencies have found out now is that a night launch is always much more spectacular. So go for a night, you know, if you're organizing a launch, go for a night launch, because photographically it looks better. Okay, so what are the James Webb and the Hubble like? This is the Hubble's mirror, 2.4 meters in diameter. And here is the James Webb mirror, which is near enough 7 meters in diameter. It's made up of 36 segments. They're not identical. We'll come to how they're sorted out in a minute. There is a hole in the middle in both telescopes. And this is very similar to the sort of Schmidt-Cassegrain telescopes that most amateurs use these days. You know, you have a light collecting mirror, which collects the light and reflects it up to a secondary, and then the secondary reflects the light back through the hole in the mirror. In the James Webb and the Hubble case, through the hole in the mirror to a set of detectors. In the case of an amateur telescope, it will be probably to either an eyepiece or a camera. But of course, an eyepiece or a camera is, well, not the eyepiece, but the person looking through the eyepiece is still a detector. So this is a large mirror. It's much bigger than the Hubble mirror, and it's going to be a lot further out in space. Officially, it's called a Korsch telescope. The diameter, effective diameter, is 6.5 meters, which is pretty big. Focal length, 131.4 meters, which is enormous. Of course, this is heavily folded. And the collecting area is over 25 square meters. That is a lot of telescope. And it will operate principally in the wavelengths 0.6, that's micrometers, isn't it? Yeah. From the orange, in other words, through to the mid-infrared. We'll go into that a little bit later. Now, I think it's interesting that this is bigger than the Palomar telescope. For most of my life, the Hale telescope at Palomar was the big lad. You know, 200-inch telescope, about 5 meters. It was the biggest, most advanced, you name it, it was the best. But these days, a telescope that's only 5 meters across doesn't actually seem all that big. Yeah, I mean, the very large telescope on Cerro Paranal in Chile has 4 8.2 meter telescopes. The Gemini combo has 2 8-meter telescopes. The Japanese Subaru is an 8-meter telescope. The 2 Kecs are effectively 10-meter telescopes. And the, I'm probably not pronouncing this correctly, but the Gran Telescopio Canarias, the big telescope on the Canary Islands, is even bigger than the Kecs. It's not much bigger, but it is bigger. So there are all these whopping telescopes around, and now they're going to put one in space, which is comparable. I mean, the Hubble Space Telescope, in terms of just straight mirror size, was about the same size as the old Isaac Newton telescope that we built back along. Because we put it in the wrong place, we put it at Hertford, and they found that sticking it in a forest was not a good idea because all those trees produced water vapor, so the sky was permanently sort of water vapor full, and they were too near the sea, and you know, they got problems with salt in the atmosphere. Never mind, like when they took it to La Palma, it did a great job. Okay, so here is the JWST mirror, 18 mirrors, not, I said 36 earlier, didn't I? It's 18. So the A segments are the inner ones, and they are identical. Then there are 6 B segments, which are in green on this, and then 6 C segments, which are a sort of greeny brown colour. So 36 in all. And of course, once you've got the experience of building one of these types, you can repeat it and do the other 5 relatively easily. Now, one of the problems is, of course, that this is absolutely enormous, and you can't readily fit anything that size into even the sort of pod that an Ariane 5 can carry. So in order to launch it, they've had to invent 2 wings. So each of those wings are hinged and hinged backwards, sort of away from you in the plane of this picture, so that the launch width is only these 12 mirrors, and the other 6, 3 on each side, are folded back out of the way. And that means, of course, that when they get to the area where it will work, they've got to fold those mirrors back into position and lock them into position. So there is a picture of the Ariane launch pod with the JWST all folded up. There is the main mirror with one of the wings folded back. The instrument segment is directly behind the main mirror. The control module is down here. There's antennae and things like that. Up here is part of the truss of the main mirror, of the secondary mirror. There is the secondary mirror, and there is the other part of the truss. This is a hinged thing, so the whole thing will, as you're looking at it, fold out to the right, while the two wings of the main mirror segment fold up to be in line with the main mirror. And the sun shield, part of it is there, and also parts of it there. So this is a very, very complicated setup, and all this lot has got to unfold like one of those fabulous films they used to do. I don't know if any of you are old enough to remember one of the interludes on the BBC where they had a stop frame film of a flower unfolding. Well, this is very much what this is going to look like. And there is a diagram of the JWST in its pod. The pod is sitting on top of the final booster stage, which sits on top of the Ariane 5, and there's the 2 boosters. So it is a very, very big effort. And the European Space Agency, one of their major contributions to the James Webb is the launch, the Ariane 5 rocket. It's quite interesting that if you look on the website now, you'll find that NASA tell you about the launch vehicle really quite proudly. But it's not that long ago where if you looked on the NASA website, you had a hell of a job finding any reference to it being launched by a European rocket. Excuse me. I think the move to a European rocket actually stuck in the American craw quite badly at first, but I think they've got used to it now. Okay, so incidentally, can you all see this, or is the what's it in the way there? I'll move it a bit. Right, so this is the sun to the Earth. You all know where these things are. There's the sun, Mercury, Venus, and there's the Earth. 150 million kilometers away from the sun. Most people react, isn't that a long way? No, it's just the right distance. We don't want it any less because we'd be cooked, and we don't want it any more because we'd freeze. So, okay, we now know where the Earth is. So this is the Earth, and there's the JWST, and there's the Moon. And just to remind you, there's the Hubble Space Telescope in orbit. The orbit is described differently according to which site you read, but this, which I downloaded from NASA, shows the orbit at 570 kilometers up. This is a fairly standard, reasonably low Earth orbit for various missions and so on. There's the Moon, about 384,000 kilometers from the Earth. And there is the JWST, 1.5 million kilometers from the Earth. It will not be at the Lagrange 2 position, it will go in orbit around it. I must say I had some trouble with these Lagrange positions when they were first talked about. And I remember when the famous and still functioning SOHO satellite was launched, the Solar and Heliospheric Observatory. And that was launched to a Lagrange position between the Earth and the Sun. And they put loads and loads of fuel on board because they thought it would take about 2 months to get into position. And it went into position like that. First try, it was in. And so they had loads and loads of fuel on board to make all sorts of corrections when they needed them ever since. That was, I think, about 1992 from memory. And it's still up there and it's still working. So SOHO has done a brilliant job. Okay. Here are the Lagrange positions. Incidentally, they're not positions where the gravity of the Earth and the Sun cancel out. They are positions in solar orbit where the net effect of the Sun's gravity and the Earth's gravity means that the position orbits the Sun in 1 year. So that, for instance, this one, L1, which is between the Earth and the Sun, should go round faster. But because the Earth modifies the orbit, it takes a year. This one, L2, should go round more slowly. It's further out from the Sun. But because the Earth's gravity adds on to the Sun's, it goes round in the same speed as the Earth. So the Lagrange position remains effectively in the same place. Now, it was found by various studies that were undertaken that it was actually safer and more stable to put a satellite not at the Lagrange position, but in orbit around it. And I remember somebody talking about SOHO years and years ago and saying that it was the first spacecraft to orbit a concept, which I thought was rather a neat way of summing it up, because there's nothing there. The way that the gravitational fields line up means that it acts as though there was a small mass there, a mass enough for something to go in orbit round it, but there isn't actually anything there at all. It's a concept, if you like, and it's called Lagrange positions because, that one is called a Lagrange position because a French mathematician with the surprising name of Lagrange was the one who actually worked it out. And this was back in, Jerry might know better than me. I think it was only around the end of the 18th century, the early 19th, sometime like that anyway. Some of these guys in those days, you know, they didn't have telly in the evenings, so they got on with some work. 1772, thank you. So, oh, that's the year of the American Declaration of Independence as well. Okay, so that was when Lagrange worked it out. As I say, they didn't have telly in the evening, so they used to do some work instead. So that's where it's going. It's going in orbit around the position. And there are quite a lot of still functioning spacecraft, Gaia for one, over there. And a few others that have been there have been put into sort of dumping solar orbits where they won't bash into anything. So there is an artist's impression of the JWST in space. I think that makes it look a bit like Darth Vader's ship from the beginning of Star Wars. This is the sun shield, of which more anon. There's the solar panels, there's an antenna, there's the command module, if you like. There's this momentum paddle there, and there is the telescope. So the whole idea of the sun shield is to keep the telescope cool. Very cool. It's I think it's less than 30 Kelvin. Now don't forget, the James Webb must be deployed for action in space. And it's a long way away from the Earth. So I'm going to try a video. I hope this will work, because this explains it with moving pictures rather better than I can do. Aha, look at that. And there you are. There you see they've used the same Ariane 5 picture that I did. There's, you see where I got them, can't you? And here is the video. Notice at this point we're only about half an hour into the mission, which is quite surprising. They've deployed the solar panels. End of the first day in space. Mm. Oh, I'm glad that worked. It's always a tense moment when you try and get a video to go. You never know whether it will. This is the emergency reserve diagram. I'm glad I haven't had to use it because although the words are very similar, most of the abbreviations are different, and I wasn't able to work out what all of them are. Anyway, it floats away from the Earth and gets into this halo orbit, and there we are. Now, the thing I want to emphasize about this, that's a very complicated deployment, and every single stage of that has to work without anybody present to make adjustments. And I think you've seen how complicated that was. Part of the testing procedure is to test all of these procedures as far as they can be tested on the ground to make sure that they are as sure as possible that they will work. And I would just add this point of caution. Up to now, no multi-mirror telescope on the ground has ever worked properly first time. They've always had to deploy gangs of technicians to actually carry out final deployment and adjustments, you know, left hand down a bit, Fred, and all this stuff. And so this is they're gonna make this work in space. They've not only got to do all those unfoldings, but they then have to carefully adjust that main mirror so that it is not functioning as 18 segments, but as one single optically almost perfect mirror. And that is one hell of a job. Although I am often in the position of Cassandra, here I have to say that I really do hope it works. Because weightlessness may be an advantage. They won't have gravity continually trying to pull the mirror out of shape. So that may be an advantage. Now, don't forget that the Hubble Space Telescope not only could be serviced by visiting astronauts, but often was serviced by visiting astronauts. I put in there in orbit 400 kilometers above the Earth's surface, should be 570, but never mind. Now, the JWST cannot be serviced like that. Its halo orbit is around the Lagrange point. It's 1.5 million kilometers from the Earth. Now, I saw Jerry nod when I said that it can't be, that, you know, this is all got to work on its own. There is no spaceship in existence at the moment that could deliver a human crew to Lagrange 2 so that, you know, somebody could apply a screwdriver at the right point. And even if there were one that could deliver a human crew to Lagrange 2, it couldn't bring them back. And it might be a lot to ask of a crew to undertake a suicide mission to adjust the JWST. So let's hope that it doesn't happen like that. Okay, here's the JWST under test. You can see that they've started separating the membranes of the sun shield. And there's the telescope, there's the main mirror rather, with the main part of the truss, not all of it, of the secondary mirror in position, and the two wings folded back. That peculiar thing over there is an overhead travelling crane. There's the sun shield, as I said. There's the 18 segment main mirror. And that, as I mentioned, is the truss. Notice that the weight is being supported by an overhead crane there as well. One of the major problems with testing spacecraft on the ground is that it can only be done up to a certain point. You know, when you launch a spacecraft, first of all, being launched is a pretty rough process. And secondly, when it gets there, it's weightless, which you cannot reproduce on the ground. So you can't test a spacecraft fully on the ground. And in fact, most of the big space missions have a considerable period of time allocated when they're in space so that the operating team can learn how to drive the damn thing, because you know it doesn't necessarily operate exactly as was expected before it was launched. Okay, that's the same thing from a different angle. Here's a drawn plan of the JWST with the folded truss there, the secondary mirror. You can see how it works. Main mirror reflects the light or infrared onto the secondary mirror through that light baffle there and into the instrument pod here. The whole idea of the sun shield is to allow the telescope, and in particular the detectors, to be passively cooled down to very, very low temperatures, which then make it effective at detecting and analysing and recording infrared. I just like that picture. I don't think it's terribly important, but I thought it was rather nice. Instantly, I love there's the side panel, the side wing folded back, and you can see those peculiar reflections in it. It's great fun. There is a main mirror segment. It is actually hexagonal, but the perspective has made it look rather a funny shape. And that's in a test. It's supported in a testing rig. The secondary mirror, which is circular and like all the other mirrors is gold coated, and there it is, partially wrapped up, gold coated, and a very interesting reflection there. Incidentally, in order to save weight, these mirror segments are all made of beryllium and then are coated in gold for the reflection of the infrared. The total amount of gold used is somewhere around 45 grams, if I remember correctly. 3/5 of 5/8 of not a lot, you know. It shows how incredibly thin these coatings are. I saw a video which I wasn't able to find again, but I saw this a few years ago, showing how the mirrors were machined. And of course, beryllium dust is quite poisonous. So these mirrors are machined under streams of water, which of course carries away the beryllium dust. Now, here is one of the important stages in getting the sun shield deployed. This was one of the first cases where a membrane of the sun shield was deployed and tensioned. During the testing, and this is what testing is for, of course, but during the testing, I don't know how many membranes they used up, but it's a sad truth that membranes kept on tearing. They weren't up to being put under full tension, which is one of the reasons for the delay. Northrop Grumman are the main contractor for the James Webb Space Telescope, and at least one commentator has unkindly suggested that with all that money going into it, Northrop Grumman should be the most financially stable aerospace company on Earth. Now, on 21st of October 2019, those of you who know your history will realise that's Trafalgar Day. The whole sun shield at last passed all its tests. Or rather, that was the announcement that it had passed all its tests. And this is possibly the most crucial test. It's certainly the one that has taken up the largest part of the delays. I didn't bother to look this time because things are more hopeful now. But when we were getting regular postponements, you know, every 6 months, the target launch date would move a year further away. I made a habit of regularly checking, twice a year in fact, to have a look at the schedules that NASA showed of how things were going, and they made depressing reading. You would have a schedule of events, and then it would say red was failed completely, green was achieved, and orange was partially achieved. And most of the time it was just a field of red with a few small greens. Very noticeably, and the European Space Agency has made a lot of this, that everything that Europe contributed always seemed to be done on time and ready, but it was the sun shield that was not passing tests, was failing in many cases very badly, and was putting back the possible launch date. But anyway, just under a year ago, that was completed, and that made it possible to start thinking of a final launch date in relatively early 2021. Now, this is possibly just a confession of my inability to understand, but I do find it difficult to understand why this sun shield is so complicated. Almost every satellite has a sun shield. The Americans have already sent up a couple of space telescopes that have used infrared. And both of them have had sun shields and passive cooling systems. Some of them have had active cooling systems as well. The difference is an active cooling system will have what is in effect a very high quality refrigeration unit, and that will use a working fluid, which is usually liquid helium. And when that fluid runs out, the active coolant stops. Now, for the length of time the James Webb is going to be up there, They cannot use an active cooling system. So they have to use a passive cooling system. They have to utilize shadows to reduce the temperature. And that's why they have all those radiators and so on. Because the detectors use a certain amount of power, around about 1 kilowatt. And that obviously produces heat, and that has to be radiated away to prevent the detectors from becoming warm and then inefficient. But as I said, almost every satellite has a sun shield. For most satellites, the sun shield doubles as the solar panel array, or put it the other way around, the solar panel array doubles as the sun shield. And it's all seemed to me that now, as I say, this may be just a confession of my inability to understand, but it's all seemed to me that the James Webb, by not using the solar panel array as at least part of the sun shield system, has made life more complicated. And this 5-layer membrane, each layer of which has to be separately tensioned, as you saw each layer separating up and then being tensioned. I mean, this is fiendishly complicated. I mean, okay, it's probably going to do a great job, but it is still very, very complicated. And it's all got to work in space. Here are just a couple of nice pics. There's the whole mirror with the truss in place. And this was actually a test that was done back in 2016, so nearly 4 years ago now. And notice that at that point, the hoped for launch date was October 2018. I think you will have all spotted that that's well past now. Here's another one. In 27th of March, oops, sorry, I didn't mean to do that. 27th of March 2018. Here is a nice picture. It's a bit fanciful. There's the Space Telescope. There's probably a planetary formation nebula. That's the sun. Notice the sun's on the wrong side of the sun shield, but there we are. Anyway, as recently, that's only just over 2 years ago, the target launch date was March 2020. That slipped quite rapidly. Oops, sorry. So there's another version of it. Notice that the appearance of the sun shield changes in each of these pictures. And now, just as an example of things that can go wrong, one of my contacts in the Open University is actually on the Space Telescope team. I mean, she's on the astronomy side rather than the technical side, but even so. And she told me that a particular delay, this was about this time, 2018. This particular delay involved 3 nuts. Now I have to stress that these are nuts that fit on the end of bolts, and that's quite important. After a vibration test, they found that 10 nuts had shaken loose. Now, again, I must stress, this is what vibration tests are for. The tests that are carried out on any spacecraft are designed to make sure that the spacecraft can stand up to the vibration, in particular of launch. If you've ever been to one of the big centers where they do vibration testing, it is absolutely horrifying. The vibration pads that they use are more powerful than the earthquake simulators that they have in geological museums. A lot more powerful. So you give the spacecraft a horrible vibration test and see if anything comes off. And in this case, 10 nuts were found. The problem was they could only find unnutted 7 bolts. So there were 3 poor little nuts left homeless, or perhaps even more important, 3 bolts somewhere not properly secured. And this involved an awful lot of very, very worrying re-examination of the entire module. Now, I don't know how familiar people are with this, but actually nuts and bolts are very important in spacecraft construction. If you see the details of how these modules are put together, it looks a bit like Meccano, which I found very comforting because I used to love playing with Meccano. I still have, over where you can't see it from here, and I have a 4-drawer chest full of my much treasured Meccano from when I was, well, I probably still played with it when I was 18, I should think. Anyway, why do you use nuts and bolts? Well, first of all, they are easily mass produced to very high quality standards, which is important. Everybody knows how to use nuts and bolts, and if they fail, they're very easy to replace. Now, you might think that welding would be better, but welds tend to fracture under vibration or impact. And welding involves local heating in the metal, and this can cause distortions. So, you know, they use nuts and bolts wherever possible. And one of the points is that the nuts and bolts produce joints which have a small measure of flexibility in them while retaining their basic structure. And this is important because it means that the structure can withstand vibration to a much greater extent than expected, not expected, but than otherwise would be true. And although I've not been able to check on this, other than I do understand that the mystery of the 3 nuts was resolved and that they were happily reunited with their 3 bolts. Now, NASA made this declaration. They often refer to it as Webb. Webb will be the largest, most powerful and complex space telescope ever built and launched into space. It will fundamentally alter our understanding of the universe. I don't know about you, when I first read this, I thought that sounded a bit bombastic. But after all, the Hubble Space Telescope, and we all remember that that had a rather shaky start. I don't know how many of you recall that famous press conference where 4 NASA officials sat there, all looking rather sick and as if they wished they were somewhere else, and they had to announce that they couldn't focus the Hubble Space Telescope because the mirror was the wrong shape. But we got round that. They gave the Hubble the mirror equivalent of a set of spectacles, and I think it's only fair to say that the Hubble Space Telescope has delivered wonders. It's long outlasted its planned useful duration, so all we can hope is that the Webb does the same. Have a quick look at some instruments. They will be in the Integrated Science Instrument module. That's the one immediately behind the mirror. So there will be a near-infrared camera and a near-infrared spectrograph. Remember, the camera will produce images and the spectrograph will produce spectra. these two instruments will work in very much the same range of wavelengths, and they are highly complementary to one another. Now, the rest of the ISM, there is a mid-infrared instrument called MIRI, and that will provide both spectra and images. Technically, it's an imaging spectrograph. They'll also have, this is all in the ISIM, fine guidance sensors, near-infrared imager, a slitless spectrograph. I meant to look up and find out how that worked, but I forgot and I didn't. So you just have to take my word for it. It's a slitless spectrograph. And there is a drawing of the sun shield, the telescope, with the ISIM. These are the detectors mounted right at the back, in effect at the prime focus of the telescope. And here is all the electronics. And then down here is the command and data handling system and the cooler electronics and so on. So this is all of it stuck on the back of the telescope. The amount of movement that the telescope can do relative to the sun shield is very, very limited. Essentially, you have to point it. You have to point the whole thing at whatever you want to look at. So the JWST operates mainly in the infrared. It will look at orange and red visible light, but mainly in the infrared, the near infrared and the mid infrared. And the reason for this is that the expansion of the universe means that although many young galaxies are blue in colour, in reality, we will see their light Doppler shifted into the infrared. So the easiest way to detect it is to make your telescope efficient in that area. The James Webb Space Telescope is fundamentally designed for cosmological work rather than anything else. And just in case people can't read that, I've done it in blue again, because we can't actually see infrared anyway. So if you want to read what I've just said, there it is in blue. Now, when James Webb produces images, they will probably look pretty much like visual images. But what you've got to remember is that most of the wavelengths that they will be using are not wavelengths that our eyes can detect. Excuse me. So I don't know how we're doing for time, Alan, but we're into the final straight. So on the 19th of August, they announced that they're going to look at quasars. This is a Space Telescope Science Institute artist's realization of a quasar. Whether a quasar would actually look anything like that from close up, I have no idea. To be honest, I don't really care. I'm not a huge fan of these artists' realizations, but there we are. Now, they announced that the Webb telescope will study some quasars and their host galaxies in 3 dimensions. But don't forget the quasars. If anyone wants to know what the acronym is, it's quasi-stellar appearing radio source. And astronomers think the quasars are powered by material falling to destruction into supermassive black holes. Supermassive means, in round figures, more than 1 billion solar masses. So we're talking about, for want of a better term, ruddy great big black holes. Now, NASA scientists have carefully selected 3 quasars, which they're studying intensely in 3 dimensions, and they call this the Q3D project. And I had to put this in. A young lady called Dominika Bilezalek, I presume that's pronounced, I've no idea. It's Polish, so quite possibly that L is pronounced as a W, but never mind. As in Lech Wałęsa. And that's a picture of her, which just goes to show that being young, female and pretty is no bar to being a principal investigator in astronomy these days. It certainly used to be at one time, but it isn't now. So three-dimensional imaging spectroscopy. What they will actually be doing is to use different wavelengths to penetrate to different levels in the galaxy that surrounds the quasar. And it's a very similar technique to that used to get 3D images, which have been done, of the lower corona or the chromosphere of the sun. So this should be fascinating stuff if they can get it going, which of course only depends on all those unfolding bits of the telescope working out in space. I'm sorry to keep going on about that, but you know, it is very important. Now, a few days later, NASA also mentioned that they've got this critical milestone, testing the command module of the James Webb so that it will be able to communicate with the Earth and pass on commands to the telescope to do what the controllers on the ground want it to do. And then 3 days after that, they showed the solar panels. As you can see, the James Webb is on a big scale. These solar panels, they're nowhere near as big as Rosetta's, but they're still pretty big. I mean, as you can see, you've got your standard chap here to give you some idea of the size of the thing. And you can see that one of these solar panels is taller than a man. So they're not small. Now, 1 kilowatt, that's what you heat something up in a microwave with. And that's the power of the largest and most technically advanced telescope ever built. I think they should have put the word space telescope. It's by no means the largest telescope, but anyway. A lot of work has gone into making the command system and the detectors work on very, very small amounts of power so that there is an absolute minimum generation of heat. So James Webb will stay energy efficient 1.5 million kilometers from the Earth. Aha. That should not be there. Not yet anyway, I apologize for that. The Webb will do some work, particularly on Jupiter, and they've chosen a couple of Jupiter's moons to look at in greater detail. One of the reasons for this is that the infrared is actually quite good for looking at the Jovian system. So there is a familiar picture of Jupiter in the background, and there is the highly volcanic moon Io. That's the one that looks rather like a pizza if you see a photograph of it. And this, oddly enough, was a picture taken by the Cassini probe as it passed through the Jovian system on its way to its triumphant visit to Saturn. Now, I thought the second interesting moon would be Europa, because that's the one that everyone seems to be focusing on. It's also the one where a lot of scientists have taken up Arthur Clarke's idea that under the ice crust of Europa, in the ocean that exists there, there might be life, because Arthur Clarke thought that it might even be intelligent life. Extremely difficult to test that, by the way, but the JWST will actually focus not on Europa, but on Ganymede. And they think, you know, results from Galileo and Juno suggest that Ganymede may have a brine ocean, a salty ocean like we have, except that where our ocean lays on top of oceanic crust, the ocean on Ganymede is under an ice layer. So it's like the Antarctic or the Arctic Ocean. So that's part of what they will be looking at. And it is claimed that these studies will not only provide us with information about Ganymede and Io, but because we are trying to find out detailed information about relatively small bodies orbiting a much larger and more massive body, they will help us interpret data which we will be receiving about exoplanets. So as you can see, this is a very ambitious mission. And that is the lot. I think I've probably gone on longer than I'm supposed to, I'm not sure. Yes, I have, but there we are. If there is still time, I'm happy to answer questions. And well, I'll leave it to Alan to explain what we're going to do now. But as I said, I'm happy to answer questions if there are any. I presume there will be.
Okay, thank you very much indeed for that. I'm sure you all found it quite fascinating. Just to really show you how big JWST is.
Oh, there's that famous picture with all the people, yes.
Yeah. I mean, that's quite staggering.
Yeah, it's huge, isn't it? Yeah.
Yeah.
I mean, this is a major telescope. It's the size of a major ground-based telescope, but it's going to be in orbit. So it is a great big whopper of a thing.
Yeah. Those, the sun shield panels, which I think the deployment of those is going to be the trickiest part of the whole thing. However, it must be said that testing the deployment of those on the ground, i.e. under gravity, is probably more difficult than it will be when it's out in space and it's weightless.
Yeah.
You can just effectively,
I mean,
and they will each go out and probably fall into place perfectly. Let's hope so. Anyway.
Oh yeah, I mean, I very much hope that it all works.
Yes, because to answer a question from Dan Miller, who said, is there any talk of a robotic mission for making corrections, assuming a manned mission is unreasonably expected? Well, frankly, the answer is no. Because of the distance, really, and getting something else to go up there. I mean, obviously, it depends on what's wrong. You know, if one of the sun shields hasn't opened properly, you've got to design something that's going to be able to go out to L2, rendezvous the telescope, which, as we said, itself is not in a particular position, but it's orbiting a position. And then what's it going to do? Have some robot arms that are going to reach out and pull these bits out into place? Seriously.
Yeah, I mean, that is a major problem. The other thing is, of course, that it's 1.5 million kilometers from the Earth.
Yeah.
And that means that the time delay is something like 5 seconds each way.
Yes.
So it will be very difficult to control such a probe from the ground.
No, you can't.
I don't think so, no. So, I mean, if something goes wrong, I mean, I understand that they have, there are actuators built into the mirror which can make corrections. And of course, there were actuators built into the Hubble mirror. So, as I understand it, they've built actuators which are capable of making corrections quite a lot bigger than they fear would actually be needed.
Yes.
So that would be it. But I think Jerry's right. The deployment of the sun shield is going to be the crucial thing, and I hope it just goes like that.
Yeah. Now,
I think we all hope that.
Referring to the sun shield, Terry Creasy asks, how does the JWST rotate to maintain a sunward direction for the sun shield? And I guess what a lot of people don't realize, and I've got to say, I didn't when I saw the very first pictures of it, is that you assume that the main mirror is going to be pointing directly away from the sun, but it isn't, because it's at 90 degrees to the sun shield. So if the sun shield's pointing at the sun, it means that the telescope will be pointing pretty much at an angle 90 degrees away from the sun. So,
but that, of course, gives it quite a lot of freedom, because the whole telescope, so long as the sun shield is pointing at the sun, the whole telescope can rotate around the axis that points at the sun. And of course, as it goes around the sun in a year, it will always be pointing away from the sun. So it will actually get a chance to look at virtually anything in the sky.
That's right. But it just,
you know, if you want to get the JWST to look at something particular, it's not going to be just a question of getting your request through the time allocation committee. You'll also have to, you might have to wait, 11 months or something till it can look at what you want to look at.
Yes.
And that might not be.
What Terry's really asking is, how does it maintain its attitude? So is it using gas thrusters or ion thrusters or whatever? And
as I understand it, that it will rely mainly on, like the Hubble Space Telescope did, on very high quality, on high quality gyros for the main part. It has got thrusters, but I mean, it's a long-term mission, and can you carry enough fuel for your thrusters? Also, because they want to keep it at very low temperatures, that they're going to not want to use chemical thrusters, which do generate heat.
Yes, indeed. So, what is the expected lifetime for it?
The optimum life is 10 years, but there is an option to expand it to 15 years, and it's pretty obvious that they are hoping that it will last for the 15 and perhaps even longer than that.
I'm sure. So that was from Karen Fitzpatrick. A couple of questions that came in you've already answered in your presentation. Stephen Helixer has asked, how could the shuttle have delivered JWST to L2, which is way past its usual operational orbit? Well, no, I mean, obviously the shuttle wouldn't go out there. It would go to low to medium Earth orbit, and it would be deployed from there with enough stage.
Yeah, it would have deployed the JWST in a folded mode.
Yeah.
In fact, an even more folded mode than it's going to be deployed in now.
Yeah. And
there would also have been a small booster to take it up from low Earth orbit to the Lagrange point. Because this is fairly standard. I mean, quite a few missions were delivered to orbit by the space shuttle. The ones I can think of immediately are Galileo and
Magellan,
Ulysses, which was even earlier.
Ulysses.
And in each case, there was a booster delivered with it.
Okay, so just a couple of other things quickly. If you want to track the launch dates of that and pretty much everything else, then I recommend as an app or website that you can go to with your laptop called Next Spaceflight. And I've cunningly just hidden that, haven't I? Right, so there you are. That's showing the details for JWST in October next year. With a lot of launches, you have the opportunity to actually watch them live.
Yeah.
And, do that on your laptop. And I stream a lot of launches here in the home. The other thing is, inspired by you, Roger, I put together a couple of pictures. I mean, normally you see the JWST pictured slightly from above, but took the image that you had and I put those two together to show just how much it is a lookalike for a Star Wars.
Well, I like that, yeah.
I'll send it to you.
Please do, yeah.
Well, thank you so much for that. A lot of detail, but not, I mean, mind-boggling in its information, but not mind-baffling, which is down to you being a super presenter. So thank you very much. I'm sorry you won't hear the applause from everyone, but thank you very much.
Well, thank you all for listening. As always, it's a great pleasure and an honour to address HAG. I've been associated with HAG, as Jerry said, and as Alan has said on other occasions, since its formation. And well, yes, it's a pleasure and an honour. I can't think of any better way of describing it. So thank you all for listening. And well, that's me done for the evening.
Except, Roger, I have a challenge for you.
Oh God, here we go.
Well, I'm sorry, but this is your fault. You mentioned this. So for the September meeting at the start of next season, which will be about 6 weeks before the expected launch of JWST, we're looking forward to you showing us your model made out of Meccano.
Yeah, I don't think I could manage that. I haven't got the skills with it that I used to have.
Come on, you've got a whole year.
Okay then, folks. Thank you very much indeed. Thank you, Roger. Thank you, Jerry, for doing that. And perhaps in a year's time, we will come back and see the work that Roger's made on his model, or at least perhaps give us an update as to what the latest delays may be. Some of you may remember a gentleman visiting us, giving us a talk, Mark Wrigley, who came along in July 2016. And Mark showed us how you could make a telescope using a 3D printer. Mark has made contact with a group of very enthusiastic students in Argentina who will be using his technology to help bring astronomy to others in their country. I got involved as I supply the mirrors to Mark, and I got in conversation with Thomas and Julieta. when I informed Thomas and Julieta about our club, they were keen to participate. And so we thought that we could give them a bit of airtime for them to tell you about their project in person. So let's, in person, welcome Thomas and Julieta from Argentina. I'm just going to find them and unmute them, and I will pass it over to them to tell you about their project. So you should now, Thomas and Julieta, the floor is yours.
Well, thank you so much,
Hi.
Alan and Roger and Jerry and everyone who maintains the Astronomy Club. Actually, the talk about the GWST was amazing. Thank you so much. Actually, Juliet and I were talking while you were presenting it, and we just loved it. Thank you so much. Well, so first of all, you might wonder, who are these Argentinian kids? And well, I'm Tomas, the guy in the picture. We are all students in a pretty big high school in Argentina. There are about 10,000 students, maybe a bit more. So yeah, it's pretty big. And Julieta and I both participate in the electronic engineering club, and the electronic engineering track, and specifically we both met in the robotics club, and we became very good friends because we were both interested in both physics and astronomy, and we just became friends some years ago. And well, Lisandro, who isn't available now because, well, he isn't available, but we are proud that he isn't available because he's actually, he will be representing Argentina in the International Math Olympiads, which is a huge achievement, and so we are really proud. And the three of us started working on this project maybe 2 months ago. That is Unicope. So Unicope started just as we are amateurs in astronomy, and as we are Argentinians, we are kind of struggling finding the necessary equipment in order to start in this hobby of ours. And we had the idea of, I had the idea of just, I can 3D print my own telescope, and I tried to design it. It didn't work out very well, so I just Googled it. I Googled 3D printed telescope. And that's where PyCon, the project from Mark Wrigley, showed up, and it actually blew my mind. And I loved it because I knew all of the technology, which involved a mini computer and all of that. So it was pretty cool. But the thing is that it still was expensive because of the computer itself. And so I just emailed Mark and told him all of this that I'm telling you now. And he was super kind and offered to help us design this new version of the telescope, which will be much cheaper. And so our goal is to be able to sell these telescopes, and with the profit, we want to donate them to institutions here in Argentina and to underprivileged communities all around the country, and probably some parts of Latin America too. So right now it's more of a startup or an idea or whatever. We are actually accomplishing some stuff, but our goal is to be a certified Type B corporation, maybe in a year or so. And Juli, do you want to continue?
Yeah. Yes. With this idea, with the start of this idea, we participated in a contest of IEEE, Institute of Engineering, and the idea of the competition was to present ideas to problematics, and we ended up winning the competition, which gave us really good feedback, and also made some contacts that are now helping, such as IBM, the company that has a program to help startups, and also the embassy of the US in Argentina. Well, they are not helping us, more like we are helping them to
to innovate in some fields. For example, they asked us to help them in order to design or to lead a hackathon, which is like a short competition in which people have to design a solution for a problem. And they turned to us for help because we have a bit of experience in that, and they saw our project. And so it was kind of amazing. We were really proud of our merits in that. They also gave us the contact of a club with an astronomy club in the south of Argentina, which is also interested in buying our telescopes. And well, then there is a municipality here in Argentina which also contacted us. Oh, because I have to note something. We haven't started selling the telescopes yet. We literally have announced that we will be producing them a month ago, and we have received a lot of amazing feedback, which means two things. First, that astronomy finally is becoming as popular as it was like in 1969 when Apollo mission was a huge deal. And that is good because popularizing astronomy is one of the best ways to engage young people in STEM. And well, Colin mentioned, well, the picture of the telescopes. Actually, if you have seen Mark's telescopes, they're really similar. We forgot to add pictures of the actual telescopes. That's a good tip for the next version of the slides presentation. And well, so this municipality in Argentina also asked us to sell them some telescopes in order to place them in the public part of the city, which also is really cool. And well, at last, but definitely not least, the biggest help that we have been receiving is Alan and Mark's, which has been amazing, and without them we wouldn't have gotten as far as we have now. And so, Juli.
Now, the thing that we saw at first when we started was that astronomy isn't accessible almost at all. Like that to buy telescopes, you need money, a lot of money, and there's also some things like physical disabilities that may not let everyone use a telescope. Also, in Argentina, our country, there are only 12 observatories, of which 6 are in the central city, Buenos Aires, and the other 6 are spread over the country, which is a really big country with many people, and not everyone is able to go to one of those observatories for the distance. So with Unicode, we are trying to make that inaccessibility to disappear, and make everyone being able to access to those telescopes and the vision of the universe, regardless their income or their physical abilities. What we are planning to do is to offer kits of those 3D printed telescopes or parts of it, and also with the benefits of it, like Thomas said, give telescopes to communities that can't afford it. We also in the future are planning to offer some science and technology workshops to encourage the curiosity from a young age. So maybe in the future, astronomy and the view from the sky will be taught in elementary school, or a kid will ask for its third eye for a telescope.
Well, so before joining the actual meeting, we had a chat with Alan, and something that has stick with me for the last couple of hours is that we talked about how astronomy is a gate to interest and curiosity about space, even from a very, very young age. And well, that since kids can't relate concepts because they don't know a lot of stuff, when they learn about space and when they learn about these planets which are really far away and these spaceships which take people to these planets and whatever, they actually get inspired and they're super excited to learn more about this. And so, for example, when Roger mentioned or Jerry mentioned how big and how similar the JWST is to the Star Destroyer, that for a child is also super interesting and excites them to learn more about STEM, for example. So we believe that through this project, we will be able to achieve, to expand the interest of STEM in the youth of Argentina. And we are trying to achieve that specifically in underprivileged communities, since it's important. Well, that's about it. If you happen to have any questions or whatever, you can mention it now. I'll stop sharing so you can like look at Julio and I at the same time or whatever.
And I can share, if there are no questions, a picture of Mark's telescope, which would be pretty much the same as ours, but with the computer that's called the Raspberry Pi. Do you want me to share? Okay. So this would be the reflective telescope, but this computer here, the Raspberry Pi, is the thing that increases the price, which we wouldn't have.
Yeah. Actually, well, Mark just now, well, some hours ago, he emailed us in order to tell us that he is already designing the new prototype, which we'll have to redesign because the components aren't the same in London than in Argentina, but it's still great that he is helping us. So the goal of this presentation was actually just kind of an update on Mark's project and how he has helped us, and at the same time how you, the people involved in this meeting, have helped us indirectly by still supporting this, and having Alan met Mark and whatever. It's just kind of beautiful that we in Argentina have the same interest as you do, and that you are interested in hearing us talk to you about this, even if you probably know a lot more about astronomy and astrophotography. Well.
Okay, well, thank you very much indeed, Thomas and Julieta. It's been fabulous listening to you. I enjoyed talking with you earlier today as well. We can see the people in our club are already applauding you. I think it's magnificent that young people like this have embarked upon such a worthy project, and we wish you well with it. Perhaps you'd like to come back next month as well, and you can tell us how things are progressing. It would be great to hear from you and get an update on it. Talking then of our next meeting, everyone, it's October the 14th, when Robin Scagel, who's the Vice President of the Society for Popular Astronomy, he visited us last year. He's going to be giving us a talk about that marvelous astronomer, Tycho Brahe, who did so much to advance the knowledge of astronomy before the telescope had been invented. So make a note of that, October the 14th. The dates will be on the club website. We'll send out the usual reminders through the MailChimp messaging service. So that's all we have for tonight. I'd like to thank you all for coming along and sharing this evening with us. I think it's been a terrific evening with so many contributors from all directions, particularly to Martin, Roger, Jerry, Thomas, Julieta, and anybody else I may have forgotten en route. So until next time, thank you very much indeed. Have a safe journey home. Bye-bye all.